Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Yes, ma'am. Yes, ma'am.
Okay, ma'am. Okay, ma'am. Ma'am. Okay. I am Sina Chako, research scholar, Department of Chemistry. I am doing PhD under the guidance of Dr. Arunas, Department of Chemistry, Christ College, Irinjalakuda. Today, I am going to talk about a highly efficient, environmentally benign one-port multi-component strategy for the synthesis of imidazole scaffolds. The multi-component reaction. One-pot single-step reaction, three or more different starting materials combined in a sequential manner to form a product. All or most of the reactants form product, less wastage, maximum yield, ideal and eco-friendly reaction. An ideal synthesis is one which is simultaneously simple, safe, short, selective, high yielding, environment friendly. Thus, a MCR can be described as an ideal one because there is readily available starting materials, simple 100% yield, total conversion, environment friendly, one pot, resource effective, safe. Why MCR are over linear multi-step synthesis? This is a four-component example of a four-component reaction. The reactant all combine to form a single product. The main advantages of the multi-component reaction is atom economy, step economy, and simple procedure. The multi-component versus multi-step reaction. The multi-step reaction is divergent reaction and the multi-component reaction is convergent in nature. Reactant P, Q, and R combine to form a single product. And the multi-step reaction is one step after another, and the multi-component reaction is reaction in one pot, and it has higher efficiency and higher diversity per step. Why look at the multi-component reaction? The multi-component reaction has wide range of application in natural products, drug discovery, and scaffold generation. The MCR enabled rapid synthesis of a complex molecule and support sustainable and efficient synthesis of natural products. And the another one is drug discovery. The MCR are used to quickly build heterocycles and peptidomimetic structures that show biological activity, making them valuable for lead optimization in medicinal chemistry. And the next one is the scaffold generation. The multi-component reaction are powerful tool for scaffold generation because they can rapidly assemble complex heterocycles core in a single step. And this is the imidazole containing commercially available imidazole containing drug. In our study, imidazole is a 5-membered heterocyclic moiety which has great importance in medicinal chemistry. In our study, mainly focused on imidazole as a core structure. These are some of the examples of imidazole containing commercially available drugs. Clotrimazole and desertoconazole, they are used as antifungal agents, and the omeprazole is used to treat gastric issues, and azomycin is an antibacterial agent, and eposartan and candesartan, they are used to treat hypertension, and misolastine is an antihistamine, and etomidate is a anesthesia agent, and allocertain is used to treat diarrhea-like symptoms. In our study, we focused on the imidazole as a core structure. The one-pot synthesis of imidazole derivatives. This is the general procedure for the synthesis of variously substituted imidazole. The benzyl reacted with the 2 molecule of ammonium acetate and variously substituted aldehyde in presence of copper sulfate as a catalyst, ethanol as a solvent to yield variously substituted imidazole derivatives. And this is the possible mechanism of the reaction. The variously substituted aldehyde, the ammonia from ammonium acetate attached to the carbonyl carbon and water molecule is removed. And then another molecule of ammonia is attached to the carbon and the imine is formed. And the lone pair of nitrogen attached to the benzyl and an adduct is formed, and subsequently water is removed and internal rearrangement occurs, and then the variously substituted imidazole derivatives is formed. And the optimization of catalyst for the synthesis of variously substituted imidazole. The first we conduct the experiment without the catalyst at room temperature. Given 240 minutes, no product was obtained, and then the temperature is raises to 120 degrees Celsius. Only a trace amount of product is formed, and the catalyst 5 to 25 mole percentage of catalyst added to the reaction mixture. And at 5 mole percentage, 35 percentage of yield was obtained. The temperature is kept constant at 120 degrees Celsius and time 60 minutes. And adding additional 5 mole of catalysts, and maximum product yield was obtained in 20 mole percentage is 92 percentage. Then we add additional 5 mole percentage of catalyst. There is no subsequent increase in the product yield. Then we optimize that at 20 mole percentage maximum product yield was obtained. And effect of solvent for copper sulfate catalyzed the synthesis of variously substituted imidazole. The solvents ethanol, water, acetone, nitrile, dimethyl formamide, and dichloromethane, tetrahydrofuran. These are the solvents used for the reaction. The maximum product yield was obtained in ethanol. It's 92 percentage. These are the synthesized compounds. The 2,4,5 trisubstituted imidazole derivative. This is chloro derivative, fluoro, naphthaldehyde, and nitro derivative. 2 nitro, 3 nitro derivative, 4 nitro derivative, and benzaldehyde derivative. And this is the methyl group, and this is the methoxy naphthaldehyde and trimethoxy group. These are the different 2,4,5 trisubstituted imidazole derivative synthesized in our lab. Majority of them are novel, and these are the spectra of the compounds. This is the FTIR spectra of the compound, and this is the H1 NMR and C13 NMR and mass spectra of the compound. And the conclusion, copper sulfate effectively catalyzed the synthesis of substituted imidazole derivatives, high reaction rate, ease of handling of catalyst, avoid the use of toxic catalyst and solvent. Catalyst is inexpensive. Thank you. Ma'am?
Okay. Sina, thank you for your excellent presentation. I have a couple of questions.
Okay, ma'am.
The first one is, you have mentioned so many advantages of this multi-component reactions.
Yes, ma'am.
Then, have you identified any drawbacks during the synthesis for this reaction?
Actually, the multi-component reaction is very simple. It is a one-pot reaction, actually this follow the green chemistry principles. The atom economy is maximum 100% is not possible. That is one of the disadvantage. But we get more than 55% of yield of product.
Okay, then you are going to use this imidazole compounds as in the medical field, na?
Yes, ma'am.
Okay, then have you done any in vivo or in vitro studies?
This is only
Or
first.
are you planning to do? Okay.
Ma'am, yes, we do that. This is the first part.
Okay, thank you, Sina.
Thank you, ma'am.
First part. Okay, synthesis. You have presented the synthesis part only.
Only synthesis part is presented here. The in vitro studies are also done. Thank you, ma'am.
Okay. Thank you, Sina. All the best.
Okay.
Hello, Sina. How this copper sulfate is catalyzing? What is the mechanism of catalysis of this reaction? How this reaction is catalyzed by copper sulfate? Can you suggest this mechanism?
This is the possible mechanism of the reaction. First the aldehyde is complex with the copper catalyst, and then the reaction is initiates. This is the possible mechanism, ma'am. Hello, ma'am.
Okay.
Thank you, ma'am.
Yes, ma'am. Yes, ma'am. Am I audible, ma'am? Okay. Good morning, all. My name is Hilda Vies. I am a research scholar at Department of Chemistry, Christ College, Iringalikoda, and I am doing my PhD under the guidance of Dr. V.T. Joy from the same college. college itself, I'm going to give a small presentation on the topic enhanced oxygen evolution reaction activity of hydrothermally tailored nickel iron LDH on stainless steel mesh in alkaline medium. As we all know that the rapid industrialization and economic expansion have driven a sharp rise in worldwide energy consumption, fostering heavy reliance on fossil fuels like oil and natural gas. This overdependence generates profound environmental consequences such as increased greenhouse gas emissions, accelerated resource exhaustion, and widespread ecological harm, which aggravate the climate crisis while highlighting the limited reserves and geopolitical vulnerabilities of these fuels. And water splitting, an electrolytic process that breaks down water into hydrogen and oxygen, offers a vital pathway for generating zero emission hydrogen fuels as a sustainable substitute for traditional steam reforming, which relies on fossil fuels and produces carbon oxides. And this is a schematic diagram of a water electrolyzer. We can see that oxygen evolution reaction occurs at the anode and hydrogen evolution reaction occurs at the cathode. And these are the cell reactions in acidic and also alkaline or neutral medium. And despite its environmental benefits, electrolysis demands substantial energy input and also incurs high cost, which fuel research into optimization strategies. And the key limitations arises from the increased over potentials of hydrogen evolution reaction and oxygen evolution reaction, which diminish overall cell performance. And compared to hydrogen evolution reaction, oxygen evolution reaction is more complex and possesses a very sluggish kinetics, which affects overall efficiency of water splitting. And this is a in left side we can see that the mechanism of oxygen evolution reaction in both alkaline and acidic medium. And I'm doing my work mainly in alkaline medium, and the blue one is the reaction in alkaline medium. And as we see in this reaction, this is a four electron coupled reaction, which therefore it is having a sluggish kinetics. So the use of cost effective electrocatalyst is critical for the industrial scale production of hydrogen gas using water splitting. And currently, the noble metal oxides like iridium oxide and ruthenium oxide are thought to be the best oxygen evolution reaction catalyst. However, high expense and their scarce resources hinders the widespread application of water splitting for hydrogen production. Therefore, the current research is focusing on non-noble metal based catalyst for oxygen evolution reaction. And transition metal oxides of iron, nickel, and cobalt have been extensively studied as oxygen evolution reaction catalyst over these decades. And nowadays, another important class of compounds which are extensively studied for OER are layered double hydroxides. Uh, that is, they are a hydrotalcite like clays, is a typical non-noble metal based material that is composed of layers of divalent and trivalent metal cations with guest anions. They are typically carbonates, and also these are intercalated between these layers. This is a schematic structure of LDH. We can see that in between the layers there are anions, typically carbonates or water molecules trapped, and these layers are made up of either divalent or trivalent metal cations. There are numerous different types of LDH, and I am focusing on nickel iron layer double hydroxide and using and analyzing its performance for oxygen evolution reaction. Coming to experimental part, I did this reaction using a single step hydrothermal method where nickel chloride, hexahydrate, and anhydrous ferrous chloride along with the urea dissolved in a certain amount of deionized water, and it is still until it obtain a uniform concentration, and is transferred into a Teflon lined autoclave. And along with I use stainless steel mesh as a substrate for the growth of this nickel and LDH. This is the obtained electrode, and it is then washed with acetone and water and dried at 60 degrees Celsius overnight and used as a oxygen evolution reaction catalyst. And nickel iron is used in 3:1 ratio, which is the optimum ratio for the best activity. And these are the series of catalysts I prepared using the different time and temperature. And coming to material characterization, this is XRD analysis, and the sharp peaks located at 11.17 degree, 23.35 degree, 34.2 degree, 38.6 degree, 60.05 degree, and 61.3 degree corresponds to 003, 012, 015, 110, and 113 planes of nickel and LDH respectively. And the XRD pattern are largely consistent with the standard XRD pattern of nickel and LDH. And the sharpness of the peaks indicate the crystalline nature of LDH. This is the FTIR spectroscopy of the prepared catalyst, which is taken in the range of 400 to 4000 centimeter inverse, and it is used to study the interlaminar anions. The band observed at around 3308 centimeter inverse correspond to hydrogen bonds in the interlayered water molecules, and the peaks at 1406 and 639 centimeter inverse are assigned to carbonate ions. The results suggest that carbonate ions and water molecules are embedded in the interlayer of LDH. And coming to electrochemical characterization, it was done in a 3 electrode setup using platinum wire as counter electrode, saturated calomel electrode as a reference, and a prepared nickel and LDH grown on SS mesh as working electrode in 1 molar KH. The electrochemical characterization is done in a potentiostat auto lab. And this is a polarization curve of the prepared electrodes. From the LSV curve, we know that the blue one, that is SN3F1D electrode, has the better oxygen evolution reaction catalytic activity, that is the one prepared in 100 degrees Celsius for 8 hours. And these are the TAFL plots of the different catalyst I prepared, and I also obtained a lowest TAFL step of 46 millivolt per decade for the SN3F1D catalyst. And next EAS analysis was performed to study the interfacial properties of the electrocatalyst electrodes. And the intercept of the Nyquist plot at a high frequency region, that is this point, represents the equivalent series resistant RS of the electrode, which originates from the internal resistance of the electrode, electrolyte resistance, and resistance of all contacts in electrochemical system. And the intercept of the semicircle on a real axis Z dash at a high frequency is RS, which is in range of 0.2 to 0.5 ohm for this electrode, indicating good conductivity of the electrolyte and very low internal resistance of composite electrode. The diameter of the semicircle presents a charge transfer resistance RCT at the interface between active component and electrolyte, which is related to diffusion of charge. And I calculate the turnover frequency using the equation Ja by 4Fm, where J is the current density at a given overpotential of 300 millivolt, A is the surface area of the working electrode, F is a Faraday constant, M is the number of moles of metal loaded in the electrode, that is a nickel and iron. And this is the tabular summary of the result. Here we can say that see that optimum OER catalytic activity is obtained for the one which is obtained from the hydrothermal temperature and time of 100 degrees Celsius for 8 hours respectively. It has obtained a onset low or onset potential of 0.4 volt versus saturated calorimeter electrode, and it also required a over potential of 272 millivolt for obtaining a current density of 10 milliampere per cm square, and it also obtained a lowest TAFL slope of 46 millivolt per decade, and the solution resistance was also very low for this electrode. A single step hydrothermal method characterized by FTIR spectroscopy and XRD analysis. Electrochemical characterization was done in a 3 electrochemical workstation auto lab with platinum wire as counter, saturated calomel electrodes as reference electrode in 1 molar KOH, and the nickel and LDH on SS mesh catalyst obtained at a temperature and time of 100 degrees Celsius and 8 hours respectively shows good catalytic activity with an hour potential of 272 millivolt to reach a current density of 10 milliampere per cm square and a small TAFL slope of 46 millivolt per decade. It also possesses the smallest RS value, that is solution resistance of 0.37 ohm, which is desirable for better catalytic activity. Thank you. Hello, ma'am. Hello.
Hilda, nice presentation.
Hello.
Okay. Audible?
Ma'am.
Okay.
Hello.
What is the novelty of this work?
Ma'am, nickel and LDH as oxygen evolution reaction catalyst was studied long ago. I'm trying to modify this nickel and LDH by doping it with several elements to
Okay.
increase its stability and also catalytic activity. This is the first part only.
Okay. Okay. Then why didn't you use nickel mesh instead of stainless steel for the growth of that
Hello.
nickel? Why didn't you use
Hello.
nickel mesh? Not audible?
Yes, ma'am. I have also used a nickel mesh, titanium mesh, and stainless steel as substrate, and I got the better activity with the stainless steel mesh because it is an alloy of alloy containing nickel and iron, which is desirable for oxygen evolution catalytic activity.
Okay. Okay. Is there any possibility of restacking of LDH? Because this
Hello,
is an
ma'am.
layered structure, na?
Hello.
Hello. LDH is a layered structure. Hello. Hilda,
Hello.
not audible.
Hello, ma'am. Hello, ma'am. Uh, no, ma'am. Your voice is breaking. I didn't understand the question.
Hilda, now
Yes,
is it
ma'am.
audible? Okay.
Yes, ma'am.
So your material LDH is a layered material, 2D material.
Yes, ma'am.
Okay.
Yes,
Okay.
ma'am.
Could you please comment on the restacking of that LDH? Is there any possibility?
Restacking, ma'am. There are anions or water molecules trapped between these layers, and actually,
Okay.
this LDH offers the OER catalytic activity mainly due to the presence of this interlayer anions or water molecules. So, restacking. I didn't read that in literature. Sorry, ma'am.
Okay, okay, Hilda. Thank you.
Thank you,
So
ma'am.
all the very best. Thank you.
Thank you very much, ma'am.
Hello, Hilda.
Yes, ma'am.
In the layered double hydroxides, it is found that in the FTIR spectrum, carbonate, a peak of carbonates are seen. Is it
Yes.
an impurity?
No, ma'am. We are adding urea for the synthesis of LDH, and typically it is present between these layers, these carbonate ions. That is already seen
Uh,
between there. That's not an impurity.
we are preparing layered double hydroxides. If it is an
Yes, ma'am.
hydroxide, the presence of carbonate will be hindrance for the flow of ions.
Actually,
Is
for
it so?
in my case, ma'am, OER catalysis is mainly based on this interlaminar anions. The presence of carbonates benefits my reaction. I don't know about other cases. Um, for my application, it is not a hindrance, I think.
Okay.
Okay, ma'am. Thank you, ma'am. Thank you, ma'am.
Ma'am, am I audible? Okay, ma'am. Ma'am, is the presentation visible? Okay, ma'am, thank you. Good morning, one and all, respected teachers. Plant diseases account for serious yield losses, and continuous use of chemical pesticides leads to increase in pest resistance and environmental pollution. In this scenario, nanotechnology offers a sustainable alternative where green synthesis or biological synthesis is highly appreciated. So, the biological synthesis of metal nanoparticles using Pseudomonas fluorescens, which is a well known biocontrol agent in case of management of plant pathogens, provides an eco-friendly, cost-effective method for nanoparticle synthesis. With that, let me introduce my topic of presentation, that is biosynthesis and antifungal potential of zinc oxide nanoparticles using Pseudomonas fluorescens. Myself, Aparna RS, research scholar at Kerala Agriculture University. So initially, identification and characterization of Pseudomonas fluorescens was done. So here, cultural characterization showed circular colonies with yellowish green pigmentation in specific media, and the fluorescence was observed under the UV light. From the morphological characterization, the isolate was gram-negative and appeared as short rods, and final confirmation of the isolate was done through molecular characterization, and it was identified as Pseudomonas fluorescens. Later, the cell-free culture filtrate of the Pseudomonas fluorescens was used for the synthesis of zinc oxide nanoparticles. For this, 1:1 ratio of cell-free culture filtrate with 10 millimolar zinc nitrate hexahydrate was mixed, and further, the pH was increased to 8 and kept at 37 degrees Celsius for 24 hours for the synthesis. White precipitation was observed. Further, this precipitate was washed for 3 times and dried to obtain the nanoparticles. Further, this was subjected to physicochemical characterization, and under UV visible spectrophotometry, characteristic peak between 300 to 400 nanometer was obtained, and when it was tried at different pH 8 came up with a good absorbance value. Further, the particle size or the hydrodynamic diameter of the nanoparticle was evaluated under dynamic light scattering. So the average size came around 346.9 nanometer with a zeta potential value of minus 27.08, confirming its stability. Further, XRD was done and a prominent peak at 31.33 degree corresponded to the crystallographic plane of hexagonal woodside-shaped zinc oxide nanoparticle. FTIR, that is Fourier transform infrared spectroscopy of the zinc oxide nanoparticle, was also done, and different peaks at 3020, 1640, 1080, and in between 500 to 600 was obtained, which corresponded respectively to hydroxyl group, amide group, as well as the bond between or the peaks between 500 to 600 was characteristic for the zinc oxide stretching vibration, and this confirmed the formation of zinc oxide nanoparticle. Further, the shape and size of the zinc oxide nanoparticle was assessed using field emission scanning electron microscopy, and it was obtained as spherical to quasi-spherical shape, and the size ranged from 80 nanometer to 41 nanometer. Further, the elemental composition of the synthesized nanoparticle was analyzed under EDS, and the elemental composition came as zinc with 44.08% and oxygen with 35.82%, suggesting the purity of the synthesized nanoparticle. Later, the synthesized nanoparticles, that is zinc oxide nanoparticles, was further evaluated for its antimicrobial efficacy against two fungal pathogens, that is Pythium aphanidermatum and Sclerotium rolsi, at different concentrations, that is 500, 750 and 1000 ppm. Here from the image itself, we can see that the zinc oxide nanoparticles was very well effective against Pythium aphanidermatum, especially at 1000 ppm, whereas against Sclerotium rolsi, it was not effective. No inhibition was observed. So this is the table showing the mean value obtained out of 3 replication as of the antimicrobial assessment. So at 1000 ppm, about 77.83% inhibition was obtained in the case of Pythium aphanidermatum, whereas against Sclerotium rolsi, no inhibition was observed. So the conclusion is that Pseudomonas fluorescens isolate was culturally, morphologically and molecularly characterized, and this was used for the zinc oxide nanoparticle synthesis, which was further physicochemically characterized, confirming its crystalline nature, spherical to quasi-spherical shape, and size was found to be in range of 18 to 41 nanometer. And when it was subjected to test its efficacy against several fungal pathogens, it was found to have potential against inhibiting Pythium aphanidermatum, but not against Sclerotium rolsi. Thank you. Hello? Ma'am.
Okay, Abarna, nice presentation. Can you go back to your
Thank you,
XRD
ma'am.
slide? XRD slide.
Yes, ma'am.
So in XRD, you have mentioned only about only one peak, but there are so many peaks in the XRD spectrum of zinc oxide.
Hello?
Could you please comment on that?
Ma'am, can you repeat it once again?
Uh,
Net,
okay, in XRD spectrum, you have mentioned about only one peak,
yes, ma'am.
but there are so many peaks
Actually,
in.
yes, ma'am. These peaks might have come because of some other impurities. Because since this is biological synthesis,
Okay,
uh, these extra peaks might be due to some other biological impurities and all. But I have seen that for zinc oxide nanoparticle, this 31.33 degree with that 100 plane at 100 uh, suggests the crystalline nature. Like this is that further characteristic peak for zinc oxide nanoparticle.
okay. Then what about the stability of this nanoparticle?
Ma'am, stability of the nanoparticle. So, as far as I have used, I am storing it in fridge at 4 degrees Celsius sometimes. Even then,
Okay,
after 1 or 2 months also, when I tried it for its antifungal activity, it is showing its efficacy.
okay. Okay, Barna, thank you and all the very best.
Thank you, ma'am. Thank you, ma'am.